Hello there. Today I'm implementing KNN algorithm, which stands for K nearest neighbors. This has two variants. It can be used for both classification as well as regression. And today I'm going to implement the classification. In the next video, I'll be implementing the regression variant of this. Once the algorithm is understood and classifier is implemented, we can extend that to regression. There's not much of a difference between classification and regression. So having said that, let's get started off with the k nearest neighbors classifier. So step 1, calculate distance between a new point P and all the other points in the data. So you have your data and you have a couple of X, you have a couple of O's, and you have your point P. Step 1 is to compute distances between each and every point. Okay. Once this is done, we sort the distances in ascending order. And step 3 would be we'll be choosing top k labels and use voting system to assign point P with the most frequently occurring label. So voting system, top k, ascending order, the compute distance. These are the keywords here, and I'll be implementing two types of distances here. One is Euclidean. So you have point 1 with x1, y1 and point 2 with x2, y2. x2, y2, and this gives you the straight distance, which is the Euclidean distance, and this is given by square root of x2 minus x1 the whole square plus y2 minus y1 the whole square. And if 2 points are represented as a vector, I think it would be a summation I1 through n xi minus yi the whole square, and there would be a square root. Yeah. So this was for two coordinates, and extend that to multiple coordinates. This formula should work. And second one would be something called as Manhattan. So take the same example. So red is Euclidean and Manhattan would be moving along the coordinates this. So Manhattan would be distance solution will simply be x to mod x2 minus x1 plus mod y2 minus y1. If you extend that to m coordinates, it would simply be xi minus yi. So distances, this there's one more uh, distance which is called as Minkowski, which generalizes both of this, and I will not be implementing this. I'll be implementing both of them separately, Manhattan and Euclidean. So this is given by um, summation is running from 1 through m, got mod xi minus yi power p whole 1 power p. So when p is 1, this distance becomes Manhattan, because you'll have p as 1 and 1 over 1, p is also 1, so you'll simply have uh, sum of all the absolute values, and when p is 2, distance becomes Euclidean. Why? When p, you have p as 2 here, all of these individual terms will be squared, sum of squared, and 1 over 2 will be square root. So you just have Euclidean there. I'll not be implementing Minkowski. I'll simply go for Manhattan and Euclidean. Well, unlike other algorithms, KNN is a lazy learner. It does not train on the entire data, because you need the p will be varying at each time, and the distances will vary as well. So depending on the p value, it will start computing the distances. So will not be training per se as the previous models that we have looked at. And this was the theory behind KNN classifier. Now for the regressor, instead of looking at the uh, target values class labels, here my class labels are X and O. Later for the regressor, instead of using the voting system, we'll be just taking the average of all the values and assign it to the P. So voting system for classifier and average value for regressor. This was the theory behind k nearest neighbors. As you can see, I'm choosing the top k. That's where the k comes from, and NN stands for nearest neighbors. We are taking sorting the distances in ascending order and choosing the top k. So we are choosing the k nearest neighbors, and that was the theory behind KNN, the math. Let's get going ahead with the implementation. Right. We have seen the theory so far. Let's get into the implementation part. Import math. We'll create a class k nearest classifier. I'll try and use sklearn as inspiration. I'll try to imitate to the best of my abilities. We'll create a skeleton first. As always, we'll have predict self, and then I know we don't need the fit method here, but I'll try to keep the outline similar to other algorithms we have implemented so far. that should do. So I had a few changes in mind. From the next algorithm onwards, I'll start generalizing this. So far, I've been taking only one input column and one output column. And also I'm thinking of setting up an animation so you can see the how the model is going through the fit process. And yeah, this looks about right. Let me add uh, new methods as we go on. I'll just consider k value as 3 for beginning, and as always you have the model which will contain all the model related data, and initially the training status is false. And for the fit method you just need x, y, yeah, and what is the x? It's nothing but list of int or float, which is the same for y as well. Later I'll change this to NumPy array. So for now I'll just let it be this x and y, and also you'll need class labels. Okay, keep this list of int or float, list of int, float, or string. Class labels can be anything. And let me put the distance type also, which will be str. And let's take key of int. Yeah, that should do. If len of x, if there's a length mismatch, we'll just raise a value error saying that x and y must be of same length. And the training length cannot be 0, so we raise a value error. Training data cannot be empty. And that part's handled. And also a few more things you need to say. I've chosen x and y to denote the coordinates of x and y for each point. So it's a two-dimensional point here, which is not the right convention. But for the implementation part, I've just considered this for now. I'll generalize for the next algorithms later. This x and class labels must be of same length. So in the conventional sense, x would be the input or the feature and y would be the target. Here both x and y are features and class labels are the target. And if distance type not an Euclidean, so, and what did we choose? Euclidean and Manhattan. We'll just raise a value error saying that distance type not found, or I'll just put distance type must be Euclidean or Manhattan. Yeah, all the edge cases are handled. Now we'll just call self KNN Yeah, that seems about right. Yeah. Mm, okay. We'll just let that be because we're not training, unlike traditional machine learning the algorithms we've seen before. So it'll be predicting for each point here. So I'll just move it here and we'll start updating self.model of x. We'll use, so since it's not this, I'll go with this. Since it's not a feature, not the only feature, I've moved x to be in lowercase. So self dot model of y would be y, and self dot model of classes would be class labels. Self dot model of training status would be true. I know we're not training, but still I'll just update it. Distance. Yep, that seems about right. And let's go ahead and return self.model. All right, let's get into the predict method. If not self.training, self dot, do I have self dot model of training? I'll just go ahead and raise a value error. And output would be self dot KNN of new input, which is our point P, as we discussed during the math, which is this point. That looks about right. Let's go ahead and return the output. Yep. And what do we need here? What is the first step? Compute the distance between P and all the other points. Calculate distance between new input and all the other samples, all the other data points. What are the distances? Distances is nothing but self.compute distance. And okay, what are the inputs we need? You need x coordinates, you need y coordinates, and you need the input. Let me go ahead and we'll just put it. Let's create the compute distance. Let's go with this. What does it take? X, y, and new input. What is x? List of integer or float, and y is also same, integer, float, and new point would be integer or float. Okay, and x1 is nothing but, oh wait, this would be this would be different. This will also be a list. I'll just keep it as is. It can be a list or tuple. X1 is this, Y1 would be the second coordinate. So if the distance type is Euclidean, we just go ahead and compute distances to be math of square root of x to I minus y to I squared x2 minus x1. So this is x2i and this is x1. So x2 between all the variables, all the data points, and this would be xi. Plus similarly you got y2i minus y1 squared at dot square root for x2i comma y2i. We create a zip of x comma y. Okay, seems to be having an error. X2 minus x1 the whole square plus y2 minus y1 the whole square, which is what we have here. X2 minus x1 whole square, y2 minus y1 the whole square. X2 is the coordinate of each point and x1 is the coordinate of your point P. That looks good. LF self dot distance type. We have already handled the distance type there. I'll just go ahead and put it else here. Else take the distances. It would simply be to the power 1. So mod this or mod that, and you will not need the square root. So let's just go ahead and create absolute x2 I minus x1 plus absolute value of y2 I minus y1 for x2 I and so yeah, looks good. We go ahead and return the distances. Alright, let's go back and compute the KNN here. We perform the KNN distance computing is done. Sort the distances in descending order. Okay. Sort the distances in ascending order. Sorted distances. We'll need indices. Sorted range of len of. Go ahead and clean this up. Distances. And our key will be that should give you the indices, and this is not this. Yeah. And here we'll be sorting the class labels with respect to the distances. Yeah. choosing the top K labels here, sorted class labels, just choosing the class labels after sorting them, and I just got self.k. Okay, initially K is 3, and we are updating it as the user passes the K value. We have the top K entries. Let's go ahead and create a frequency map. Frequency map is an empty dictionary for in top K labels. Frequency map of I would be frequency dot get I comma 0 plus 1. Yes, this should create a frequency map. Choose the most frequent class label. So here's the part, right? So here we are choosing the class labels. In Regressor we would be choosing the values, and instead of choose top K entries, and instead of creating a frequency map and finding out the top K, the most frequent label, will just perform average, get the mean of all the values. So most frequent label would be maximum of frequency map, and the key would be passing as frequency map dot get. Seems good. Frequent most frequent label. This is what you will be assigning it to. The prediction of the new point. Looks good. Evaluation, I think I should start moving this to a separate file since we are using this a lot. Again, if len of what does evaluation take, we'll take X test and Y test. If they don't match, simply go ahead and raise a value error saying that X test and Y test must be of same length. If len of Y test just copy this. Testing data cannot be empty. Yep, that looks good. What are the Y predictions? We create an empty list for I in X test. We call the prediction method here. Prediction self dot predict. Where did the predict method go? Yep. Yeah, looks good. Okay, self dot predict of I. You append that to the prediction list. That looks good. Accuracy is what? Self dot accuracy score of Y test and Y pred. Let me go ahead and change this for, no, I'll just let it be. Why change when it's working? And accuracy is, I'll just round off this to 2 decimal points. Yeah. Choose list of int. That looks good. Uh, yeah, I'm not using NumPy yet. If you have NumPy, you can just do np.mean and I should be getting that. So scores whenever ytest and yp equals 1 or equal, you just give 1, otherwise 0, and sum them over to get the scores. Accuracy is nothing but scores by m, or if you put it nicely, 1 over m star scores. Alright, that looks good. Return evaluation metrics. Okay, that looks good. Let's go ahead and test it out. I'll take a simple data set, simple, very simple. And this is where things will start changing from the next algorithm, which would be support vector machine. We'll start importing real life data set and start testing it out on that. We'll take 3 A's. Create an instance of our class. And we'll start fitting that here. Got x and y, and class labels. Okay, let me do it this way. X is x, y is y. Class labels is class labels. Instance type to be Euclidean. And let me choose k as phi. So let me check the prediction for 4453. That seems good so far. Let's create x test. You'll need tuples. We'll take 2277. Just keep it symmetric. Y test to be A, B, and B. I've taken this at random. Print. Notice the training data and test data are different. So there is no data leakage like before. Alright, that looks right. So let's just go and run it out. Where's the issue here? List of integer and float. We'll just remove this out. Timing. Out. Okay, let me just choose a different interpreter. Predict method is throwing an error. Seems to be the problem here. 4453. Okay. Predict method is throwing an error. New input is this. Okay, we come here, self dot k. This was not necessary. Yeah. Accuracy is 0.67 and the prediction happens to be B. Well, let me refine this a little bit. An input is this. Output is this. Yep. Predicted output is this. Not output, predicted output is B and accuracy is 0.67. And let me have a, okay. Let me put up a representation. Yes. So you got training status to be true, X, Y classes, and distance type to be Euclidean. Let me change this to Manhattan. Later, once we have gotten to a certain level of code modularization where I have moved accuracy score and the visualization part, all of that to a separate file, we'll start writing testing scripts for automating our tests here. And Manhattan looks good as well. Alright, so that was implementation of KNN classifier. In the next video, I'll just extend this logic to regression part. Yes, thank you.